Hey folks, it's Chris with Microsoft, aka Big Daddy Nines. Welcome to another exciting episode of the Performance Series. So in the last episode we covered virtual address space and we started drawing this pretty little picture up here. Hopefully you're not joining in this particular episode. Go down and click the link for the previous one, or just start the whole series in the link below and start looking at that, because that was covering the whole beginnings of the concept of virtual address space. We were covering almost all about the user mode. This time we're going to be talking about the kernel. So virtual address space is just as fake to the kernel as it is to user mode. And that's an important concept to understand, because while every single process that's going to fire up on your box here in user mode has this same virtual address space, they have their own same 2 gigabytes of space that they can get on a 32-bit system, or 8 terabytes on a 64-bit OS. The kernel itself only gets the one. Right? We don't have multiple kernels. We only have one kernel. And so what we are going to talk about really quick here is the construct of, what it looks like to be up, down in that area. So let's just draw a couple more little lines here, if I can get my mouse to cooperate. Let's go in and pop a little line right here, and let's pop another one right here. And then we've got a big area down below. So these I'm not drawing to scale, obviously, but page table entries is a small part of the kernel. In the previous episode we talked about how the page table entries will give us some space to keep track for the virtual memory manager here, to track all these memory reservations and who's actually touching memory and needs to get some mapping over to some physical address space. There's a couple other sections inside the kernel other than the PTEs. The PTEs is actually a very small part of what is in the kernel. One of them is called the non-paged Poole. And you'll see that sometimes being referred to as the page, the non-page pool, or page non-pool. There's a lot of different ways that it's documented, and let me get that green so we can keep it the same color. And then we've also got, not surprisingly, if we have a non-page pool, we have a page pool. It's a little bigger. And it's a section inside of the memory here, or the virtual address space for the kernel, where drivers live. So this area mostly is that's not a circle. That's a circle. This area here is mostly about drivers. It's got other stuff too. The operating system keeps some things in here too, but you've got a whole lot of drivers that run in this space so that they can talk to the hardware, and you get filter drivers too. So like your antivirus, it lives here, and a lot of times the non-page pool, the page pool, it fills up and it can lock up a system, especially on 32-bit operating systems. So page table entries, we can run out of them. So we're going to be looking at that a little bit as well, and we're going to talk about those for the most part, because those are the things that we run out of the most. The rest of the kernel is made up of the system, cache, resident bytes, residenti, and the PFN, page frame number database, and DB, and let's just say and stuff, because it's not real important to get into a whole lot of discussion about that. We've already talked about system cache resident bytes, and this is just for illustration purposes, because in the episode where we were talking about the system cache, I told you a lot of time, one of the most common things I see this consuming large amounts of the kernel is a result of a bad disk. Is probably the most common one, and the system can't write and has to cache the stuff that's supposed to be getting written to the disk, and it'll consume as much as a gigabyte on a 32-bit OS and a terabyte on a 64-bit OS. And so that's really kind of important to kind of keep in mind when you're running out of RAM. But we're not talking about RAM. Again, this discussion here is much more about the fake address spaces, right? So we're gonna be talking about that one in this discussion. So most of the stuff today is going to be this stuff up here, right? Because when you see the condition of a locked up server, you can run out of physical RAM, you can run out of RAM and page file, and the system becomes non-responsive. You can barely get the thing to go Control Alt Delete if you're physically at it. You can't remote desktop into it. This also when you run out of any of these three things, will cause your system to have a similar condition as though you ran completely out of RAM, even though maybe you haven't, right? So you're going to look at RAM first because that's really common. You're going to see you still have RAM, still got your your committed bytes percentage didn't ever hit 100. Your available megabytes counter was still sitting at several hundred megs, maybe, or higher, but you're still suspecting a memory leak condition because the thing just kind of locked up. Another thing to be really cognizant of here, something to be watching for, especially with these two guys, when you see a server or workstation lock up on a regular basis. So, for instance, every 3 days, or every 1 week, or every X number of hours, the system becomes completely unresponsive. You have to come power it off and bring it back up, and it runs great, and it runs just terrific for a really long period of time. And then again, after X number of days, once again the system is unresponsive and you have to go shut it off or something. That's because potentially you've run out of your page pool and non-page pool. A lot of people will say at this point, especially when I'm teaching this as a workshop, they'll say, well, Chris, we're on 64-bit now. We don't really need to talk about running out of page pool and non-page pool and exhausting page table entries. Bull. I have worked a lot of cases, and I'm not even a PFE anymore. I have worked a lot of, that's a premier field engineer, that reactive guys that go in the field. I still see this come up in customers. And 64-bit OS, huge amount of room, but yes, you can still run out of these things. Yes, you can get really crappily written drivers, especially antivirus drivers, and I'm not trying to pick on those guys at all, but they are the worst when it comes to managing resources in the kernel. And now that they know that their stuff's running on a 64-bit OS, they seem to have gotten careless, and I'm seeing a lot more non-page pool and page pool exhaustion cases coming up. And there are counters that you can use to measure all this stuff. So we'll cover the counters, and then we'll actually go and look at the stuff here in a second in a live system, and we'll reproduce some crashes and stuff. But so the page table entries, this is a counter that tells you how many you have left, and you're typically just fine until you start running under about 12,000. So that's where you really go into a warning, and then under 8,000 of these, you're going to go into red alert mode. You're going to go, hopefully if you got like monitoring set up like SCOM or something, that's where you need to be alerting, because the system is about to crater when you get under these. Now, I will say page pool, non-page pool, a lot better. In 64-bit, we don't see nearly as many cases as we do with 32-bit operating systems. They're still there, but they're a lot lower, but that's still a primary indicator of a resource condition. But I have to say, page table entries, I have not seen a single one of these yet. I haven't talked to my buddies to get specific numbers of how many they are, but I know that there's not much of that. There's also some thresholds we need to be cognizant of with the non-page pool. That's a good way of just saying the stuff where the drivers live that is in RAM, versus the page pool, which is the stuff where the area where the drivers live that is not in RAM, even though that's way oversimplification. The non-page pool is, on a 32-bit operating system, is going to be 260 megabytes is all that the system pretty typically is going to be able to support. If you go over this or approach 80% of that, anywhere in that area, if you start seeing that on a 32-bit system, and you're not seeing the wrong numbers here, guys. I'm very serious. 260 megabytes is a problem. Really serious problem. And if you have an OS that's up to that limit, then it's probably crashing. And I told you that there's not a lot of room in this 32-bit kernel. Get off that sucker, man. So that's your threshold for a 32-bit system. But there's there's a couple of different counters I want to give you here, and I don't want to make this super complicated, but there's a couple of different numbers that really come into play, and it has to do kind of with how much RAM you've got in your box. So when we're talking about the non-page pool, if you've only got like 2 gigabytes on a server, which I see that in virtualization fairly commonly, your non-page pool is only 900 megabytes, so it didn't help a whole lot, guys. So this is why it's still running out. But let's say that you do actually have a 4 gigabyte system. This sucker's not going to get any more than about 1.5 gigabytes, and then we'll continue this going out to 8 gigabytes, and on 8 gigabytes now we're seeing some free space here, so we're talking about 3 gigabytes that you can go up to. And then let's just take one more, and we'll say with 16 gigs, then we're now of RAM on the box. At that point, with 16, you're now going to see about 6 gigabytes that you can get up to in your non-page pool. So important to be paying attention to these numbers, because and I'll put all this stuff on a chart for you later. But yeah, 260 megabytes on your 32-bit and 900 megabytes on a 64-bit that only has 2 gigs of RAM in it. I just got a sidebar for a second to say everybody's gone a little bit overboard with this whole virtualization thing, and you're creating VMs that have user workloads on them that are running Windows Server that are less powerful than my phone. My phone has got more RAM and more processors than a lot of people are putting into these VMs these days, and it's kind of sad in a way. So then obviously we have to go into the page pool and have a discussion about that as well. So the page pool, you get a little more breathing room, but not much. We're 360 megabytes for the 32-bit operating systems, and then when we bump that up to similar examples here for 2 gigabytes of RAM on a machine, then you're going to have about 3.5 gigabytes before you exhaust your page pool. Or if you had 4 gigabytes, then you're looking at about 5.5 or so is what it usually runs up to. And then let's just continue this out so that we have the whole list. At 8 we get about 12, and then if memory serves at 16 gigabytes on your server or client or whatever you happen to be, this one really jumps up. It gets kind of ridiculous. We're at 38 gigabytes at that point for your page pool, which hopefully you don't have drivers that are taking that much up, but there you go. So those are kind of your thresholds. This is where you're going to be as far as when you start to see server problems. Now again, just like in the user mode, we do have to allow for some fragmentation, so don't expect to be able to ever hit these theoretical maximums. You're never going to be looking at probably more than about 80%, 90%, or even in really rare circumstances where you saw this thing crash earlier at about 95% on the user mode when we were getting up there. And so those are the biggies. Those are the ones that are going to cause systems to crash in the kernel, and again, it'll kind of make the system unresponsive. You'll probably, if let's say you had a client system that was doing this with a keyboard and a mouse, the mouse will move, and the keyboard, you can change the caps lock light on, which is usually a really good indication that you don't have a hardware problem, even though people very often interpret these as hardware problems. And then we start to throw hardware at the problem. Very, very commonly, I don't even get called into these, or when I was at PFE, I didn't even get pulled into these type of cases until after the customer's very frustrated because they've had this problem and they've thrown hardware at it and spent money on it, and they're wondering why the problem hasn't gone away. Since these counters are all measurable in the OS, giving you the exact numbers are not super important, because you can just see the pattern, especially if you're running a perf counter in like a black box or something. What you'll see is them run up to these numbers or near about them frequently every time it crashes, and since these are usually easy to reproduce, even though they're sometimes time consuming, you'll always see the same pattern. You'll get around one of these numbers, and I can get you a full list of numbers, or I can show you how to actually get these numbers, and that is a couple of steps that are involved in that, and I'll probably have to do that as a written blog, but just as a really quick overview, since I'm not sure if I'll do a video on this or not, you can see the exact numbers in the counters with Process Explorer. You don't see it out of the box. You have to get the dbg help.dll that comes with the Windows debugging tools, the debugging tools for Windows, and you can point Process Explorer at that and then configure your symbols like you would a debugger. And you know, once that's in, when next time you relaunch Process Explorer, it'll actually tell you the cap of what your virtual address space for your page pool, your non-page pool actual limit is on that system. So one other thing I should note is that, I was talking about how people will buy memory to try and solve these these problems and stuff. Ooh, I just figured out how to make that bigger. On these 32-bit systems, I did that, and then I didn't do the cool thing of going over to the pen and making it bigger. There we go. So these 32-bit systems, what's really funny is when you add more RAM to them, they actually have a tendency to get a little smaller, because you have to come in here and do this page frame number. Because remember, the page frame number is a mapping of all of the physical memory address space versus this virtual address space. This is all the little bits and stuff all addressed out to explain how much RAM is physically on your machine. And if you're having to put a database to map all that stuff, then you've taken up more space by adding memory. So people will actually have a problem that's happening every 3 days, and then lo and behold, they go buy some memory because they think they have a memory problem, which they do, but just not the right kind of memory. And then they've spent money on that problem, and they therefore go in and create a bigger problem that now is happening every day and a half as a result. So it's kind of sad, but it is very, very common. Okay, so let's come in here and take a look at a running system. Now you can actually see in Task Manager where you're at as far as the page pool and the non-page pool. It's all listed in Task Manager right there. Okay, no aim today on my pointer, sorry. But this wow, there we go. Couldn't get it to zoom back out. So this is where you can see it live, and that's in Task Manager. But where was I going to go here? Oh yeah, perfmon, and it's up. Yay! Obviously, in most cases, when you're troubleshooting a memory leak, especially one that's crashing the server every 3 days, you don't want to look at the server for 3 solid days trying to figure this thing out, right? So let's just reuse an existing counter here, and since we already know what we're kind of looking at, there's no reason not to cheat. So all under memory, we've got the 3 major guys that we were talking about. They're all listed right here. We've got our you can't see that when it's all blue. Alright, so we've got our system cache. Oh, we're not doing a system cache. Let's go up and find the page non-pool bytes, and then we're going to find our page free system PTEs up here at the top in the Fs, CDE, free system PTEs, page table entries, and then our pool non-page bytes and our pool page bytes, and we're going to dump those 3 in there. And then we're going to throw in something else that is, oops. You know what? Let's throw a couple of other things. Let's go ahead and throw our %committed just to show that this doesn't actually cause us to run out of available megabytes or our commit limit. And well, as much as I regret putting this in here, I want to show you what it looks like, but also say that this doesn't always work. And let's go to Processes. And let's throw in counters for our pool and non-page. I'm going to go ahead and throw these in here, but I'm going to have the discussion with you right now. The kernel doesn't have user mode processes. All of this stuff here that we're looking at on the left side, these are all user mode processes, okay? And when we're measuring things like page pool and non-page pool, user mode processes don't live in the kernel, right? user mode processes live in user mode. So this is doing just a little bit of funky magic going on here to try and tell you how much Poole and non-page Poole is being used inside the kernel, even though they don't exist inside the kernel. So kind of take this with a grain of salt and don't try to rely on these to tell you who broke your box. Right, so it's important to point that out. So those are our main things to track a kernel memory leak, or at least see one going. So we'll go ahead and kick this off and make sure that counter's running, and it is running now. And we're going to fire off a system test called not my fault, and we're going to do the leak function, and we're going to let's see, do we want to have kind of task manager up here and have it, if I could find task manager. What did I go and close task manager? Lovely. Let's get it back up here. And since it's actually able to do some live monitoring of that, performance, memory. Now this is a 64-bit operating system, so if I had a 32-bit OS that we could use, then crash the box that way, then terrific, we'd go ahead and do that, but we don't have that. We also don't have a counter for showing free system page table entries. Lovely on that as well. But okay, so let's leak non-paged, and we should start seeing the non-page Poole going up. And see that we're going up by 1 meg at a time. Obviously that would take a little while, but it's now showing us here on the left side what it's leaking. So we're at 16 megabytes, and over here we can see that we're going up, and so we should be able to track that a little bit in perfmon and see that that is going up. But you can also notice that our memory utilization not really being affected a whole lot. You can see it bumping up a little bit here and there, but it's not actually leaking super big time. And so let me go ahead and stop leaking, and let's leak that a little faster. And since it's 64-bit, let's leak it in crazy amounts. So there we go. Now you can see we're actually taking up some RAM at the same time, because obviously this is non-paged, and because it's non-paged, well, let me go ahead and see if I can stop that and let go of some of our resources. Because it's non-paged, obviously it can only be backed by RAM. Drivers very commonly are in the smaller non-paged Poole area, and the reason that the drivers like to live there is because, let's say, stock your video card driver, right? That thing needs to be able to respond very, very quickly. It needs memory. It needs the ability for the processor to get quick access to it to do things like render graphics on a graphical user interface. Kind of important. So there we go. All right. So let me just cancel out and close that, and let's just kind of look really quickly at what we see in perfmon. Go ahead and stop this counter, let the system kind of recover a bit, just a bit. Let's go to our blue cube here. Oops. Why do I keep clicking that green box? Out of habit, I guess. So let's remove that. Let's grab make sure I'm getting the right one here. Yeah, memory test 3, second test, get that in there, pop it in, let's add some counters, and let's look at and see, let's just throw them all in there. We'll just look at all our memory counters really quick and see what all happens. So since these are unlike counters, we will go ahead and scale them so they'll all fit on there so we can see some patterns. So here we go. Poole paged, as you can see, is not doing anything. We can see that the Poole non-paged went up, and the percent of committed bytes went up, and free system page table entries stood still, and available megabytes. So Poole non-paged was, once again, it's important to look at things like maximum in a counter like this, and it looks like we were at 1.3 gigabytes or so before the system kind of got as heavy as it possibly could, and I told you it was probably around 1.5 gigabytes in a box like this in the counters below, and then we have the overhead of some fragmentation and whatnot. So there we go. Now let's go ahead and dump these out, and let's go look at the processes. So we know that it was the non-page Poole So we only care about the non-page bytes, and we're going to throw in all instances and get them all in here. And let's see with that one, we had total, and then let's look at the graph from, I don't know, maybe put it at 10 since these guys are all so small. Yeah, see, I don't see one leaking here, and I'm guessing you don't either, right? So it's one of these days I'm going to fully understand why we even have this counter, but it's not showing me leaking non-page Poole because these are user mode processes, right? So problems, right? Now if I do the same test on the page Poole, it's going to look exactly the same. So I'm not going to insult your intelligence by spending minutes doing the exact same test, but instead this time, running the Racinovich tool with a leak in the paged. So it works the same way. And anyway. Okay, now so we're going to look at another tool. This is a bit advanced. I even considered possibly not putting this into this series because it gets a little thicker. This guy's called poolmon.exe. You can get this from several different places, like the driver deployment toolkit, the Windows SDK, several different places, and it's kind of an interesting little tool. As you can see here, we've got some data available to us that's kind of hard to read and difficult to understand. At the moment, this is all sorted by alphabetized at the moment. So you can see there's these little 4-digit things over here. These are called tags. You can see that they're noted as paged, and you can see that they're noted as non-paged. So non-P and paged, those are those indicators there. And then there's a whole bunch of other stuff out here that we're not going to talk about today. And then over towards the right of this screen, you'll notice that we have this this piece called bytes right here. So if you were looking at this for the first time, and that's the only pieces you were looking at, you'd probably assume correctly that this is a measure of the number of bytes of something that's running in the page Poole and the non-page Poole. These tags, that's what lives in the page Poole. These are filter drivers, these are device drivers, these are handfuls of other things that are going on in the kernel of the operating system. And since these all live in the kernel, all of this stuff here that you see from this list over here, and one of these days I'm going to remember how to zoom it correctly, or at least use my pinky to hit the right key, but all of these pieces and parts are what really lives in the page Poole and the non-page Poole inside the kernel. And when you're looking at things, as we discussed in perfmon, you're not going to see anything that's in the kernel from user mode. And that's the real key here, is that when you're measuring stuff in perfmon's a user mode process. It measures user mode things, and you're going to get user mode data. So even though there's a non-page Poole and a page Poole per process counter inside of the process object, that doesn't really do you a lot of good. So let's talk about some of the things we can do in here. The most important one is B, the key B. We'll sort this by bytes. And now what we're doing is we're sorting this entire screen by the tag and the bytes. Well, sorting by the tag and sorting by the bytes and viewing the tag. So the important things to note here are the name of the tag is CM31, and bytes right here will tell us how much of the paged Poole CM31 is. So from this, you can determine on a live running system, if you have a kernel memory leak, which of the processes are taking the most of whichever you're leaking. So if I'm leaking page Poole and I come in here and I see this guy, well, it's not necessarily him, but it's a good indicator that he's the biggest one. And the big thing that's going to tell me whether he's what's leaking is if I come back later and he's quite substantially bigger, and he keeps getting substantially bigger until we finally see the system crash and it's out of page Poole in this case. So then I need to go figure out who in the heck is CM31. So that's when you start having to do some internet searches. Now, so scenario would be, we've got the perfmon, we've looked through the primary indicators of a resource condition, where we have some sort of an exhaustion that's going on in our system, and what do? Well, if it turns out to be non-page pool or page pool or whatever it happens to be that we're leaking, then we need to determine what it was. Now, perfmon's great because it can measure things over a period of time, but since it can't measure this, we get into a more difficult discussion about how we're going to go find out what what system process is killing you. So, as I previously had indicated, we will see these things leak out over a fairly what's the word I'm looking for? Regular, I guess, period of time. So if it crashes the system 3 days ago and it took 3 days before that, then it's probably going to be another 3 days. And if you're on day number 2, you can come in here and start looking at these. And if it's a slow leaking process, which they usually are, this will be continuously, one of these processes will be continuously getting bigger over time. And if it's a quick spike of a process, we get into a different thing that you've got to do, and you got to come in here and let me show you a trick. All right, so let me zoom in here on a live zoom, and we'll kind of look at a couple of quick switches. If I do a poolmon with a like that, it'll tell me that these are the things I can do. You can see that an N will do a snapshot, but it'll do it to a log file. I don't even have to give it a name. And then I can also additionally sort that by bytes with a -b. So really simply just a -n to log it, and then a -b to do it by bytes. So if I do this, it's going to dump everything out to a text file for me. And I've already done this a couple times to show you how you could do this several times. So we'll go in here to pool snap, which by default is the text file it'll put it into in the working directory wherever you have poolmon at. And you can see it's just kind of a screenshot of what we were looking at in the live view. And you don't have to have poolmon already running to run this. And it'll just dump everything in the kernel out here. And it'll be sorted by bytes. So as we get down lower and lower and lower, you'll see we get to the zeros. And then you'll see all of a sudden we snap in again. So without any additional switches or doing anything extra, what we will get is a time value here of an appended text file with time value. It doesn't tell you what the time is, it just tells you, here's the next set. So it just keeps on appending to this file. And if you were to do this, say, every 20 minutes or 30 minutes or 5 minutes, depending on how quickly you're leaking, you could wrap this little command up in a batch file and put a sleep command or a wait command or something on it and just have it keep snapping every 5 minutes, 30 minutes, whatever you do. The thing will get pretty big pretty fast, so you want to be a little bit cognizant of how often you're doing it. Don't set it off for 30 seconds if it's going to leak for a week and then you've got a text file that's a gig and you can't open it with Notepad and look at. But what you're looking for is something that's increasing in size. So let's simulate that really fast. And I do want to talk about some things that you've probably read about on the internet when you're troubleshooting these. One was called the Poole log analyzer tool. You'll need to look at Notepad because this is a very, very old tool and people still refer to it to this day. But it requires a really old version of .NET. As you can see here, it wants 1.1.4322. It's a little flaky. When you can get it to work, if you can even find the tool, which is really hard to do because it was written something like 10 years ago or 14 years ago. It was right around the time Windows 2000 came out, well, a little bit after that. It was early 2003 days, I want to say. But the tool is very hard to find, and it's very flaky. All it does is graph the stuff in a text file, which you can do anyway. 90% of the time, you won't need any of this batch filing or anything. What you'll be doing is coming in here and you'll notice, hey, I've got this system, locks up every 4 days, going in, looking at it today. I can see CM31 is right here, and then I can come back in an hour or two or tomorrow and I look at it and it's much, much larger, and it just keeps getting larger until finally it crashes the system, and that's how you'll solve most of them. The only time you really have to automate this stuff is if it's just a spike condition where everything's fine and then over a period of just a few hours it goes through and consumes all your page pool or your non-page pool or something like that. And then you're going to be going out and you're going to be doing Bing/Google searches for this. If I were to Bing/Google search on CM31, I would find out that it is configman. That's my configman client. So you system center people, this is what's running in the kernel on your people's clients. It's a tag called CM31, and you are already aware of a user mode process that you install. It's a client that sits down in the system tray, or can be hidden, whatever, however you configure that. But there's really a kernel operator that is going on, and mostly what the client is doing is communicating with this guy who actually has full kernel view. So a lot of Bing and Google searches is what's in your future if you are leaking on a tag. There's an additional tool that you can use that comes with anytime you download any of the Windows debugging tools or any tool similar to that. You'll typically get this little guy in here called pooltag. The pooltag is just a list of Microsoft tags. This is all the tags that Microsoft use. So if we have, let's say, MMST, I can come in here, do a quick search, say MMST. If it comes back and says not found, you know that you're looking at somebody else's tag. If it does find it in here, then you can see that it's a Microsoft tag. And in this case, it's MMT's section object prototype PTEs. I think that means that it's probably the system PTE process that's managing the virtual memory manager. Don't know that for sure, but I know now that this is a Microsoft tag. Now, 90% of the time, 95% of the time, these are made up figures, but in my personal history of troubleshooting memory leaks, what I typically find is that the Microsoft tag, if it's leaking, it means we haven't run Windows updates in a while. Microsoft has already fixed the problem and we need to get patched. What you will usually find is a control F, and you'll find that the leaky tag does not exist in this list, which means you're going to have to do some research to go find out who it is. Maybe it's antivirus tag that's leaking or something along those lines. Okay, so let's take a quick look at doing this. So I'm going to run the not my fault program again, and we're going to fire it off, and we're going to go ahead and simulate leaking some memory. And that's in this tab here. So let's pop a 0 in there, get our poolmon going, and let's leak. We got all these page stuff up on the table, so let's leak non-page pool. And so we should pretty quickly start seeing a process in here called leak, and it'll appear in the list. And there it is. It's already up almost to the top right here, as you can see. And watching this live, you can see it's up to 102.400, and now it's 1536. So now it has very quickly become the largest of my non-page pool. In fact, the largest thing running in the kernel between the non-paged and the paged, and it'll continue to do this and leak out as we go. And if we were to run our little guy here and dump out another snapshot into our poolmon and let this thing continue to rise up, it'll continue to consume it until there's nothing left to consume on this box. So we're getting up there. We're now at like 500 megs, and eventually we're going to lock this system up. But we'll get us a couple more little snaps and kind of get a view of what live running poolmon looks like. Now he's up to 600, looks like. So just for the heck of it, we'll throw one more in there. We'll go ahead and stop and cancel so that it releases the system. We'll see it disappear out of poolmon, and there we go. If we pull that file up again, we should see, not counters, we've used that already, pool snap, and we'll see we had CM31, and this one was the biggest guy, so we just kind of scroll down a little bit. Did I miss him? No. Yeah. CM31 was the biggest guy here, and then actually I could even use some magic. Since we know CM31 is consistently the biggest, I just do a search, and now I see that he's not the biggest down here at the bottom. We can now see that he's appeared. Maybe some process in the real world has now kicked off and is running some thing that happens only in the middle of the night. Let's go ahead and find the next one. We can see that now the number is quite a bit bigger. Well, now the number is quite a bit bigger. And we go down further in the text file, and now it's bigger, and that's just a textbook memory leak inside the kernel right there. We can tell it's a non-page pool. We can tell what the 4-character tag is for that process, or for that tag, 4-character tag label. and that's the end of that file. But this is, this is what you're looking for. This is what you're going to see when you're running out of page pool. This is the easiest way that I know of to go and troubleshoot this stuff. Again, probably 80 to 90% of the time you're going to be seeing a slow leak condition that you can catch if you just come in here and look at this thing every once in a while. These usually take a while to leak, so typically you're going to see this happen over a period of days. At a minimum, it's a handful of hours before this happens, so you at least have the time to come in here and see a pattern forming. And again, if you need to set up an automated process, well, just ditch this thing out to a text file every once in a while and just have this thing, on a batch file looping around and pushing you out. So other things that you might be looking for when you're running out of page pool or non-page pool are event ID 2019s and 2020s in the system log. Those typically will appear whenever you have an exhaustion of page pool or non-page pool. Another couple of quick notes. I'm not going to go into a lot of detail on this because nobody does this really anymore. But if you're still running some older systems out there that are 32-bit, and you've heard of things like the 3GB switch, remember that pretty little picture that we were looking at before? When we start talking about modifying the virtual address space, there are some cautionary notes I have for you. Switching quickly back to the diagram, we talked about how we had 2 gigs of virtual address space over on this side of the fence over here, and then we have 2 gigs here. When you guys throw that 3GB switch on a 32-bit operating system, what you're doing is you're cutting the kernel down to 1 gig, and then you're giving your user mode 3 gigs. Now that might sound great for your user application because, wow, now he's got 3 gigs, but your kernel has only 1. Now remember, this is 3 gigs for every single process that's running on the system. That isn't shared by all the processes. I have to reiterate that. But this is not shared by anything. This is the kernel. The kernel is now limited in its non-page pool and its page pool and its page table entries and the resident bytes, all down to this 1 gig. Now that can be tweaked with that user VA 3030, and we're not going to go into that. That just causes us to go a little bit more to the kernel and a little less to the user mode. But when you start tweaking like these, you have to be very cautious because people will turn that switch on hearing, hey, we've got a kernel memory leak. Let's go through on the 3GB switch, and you literally just cut your problem in more than half because it actually sacrifices a lot of these guys over here first, and we wind up with nothing left a lot sooner. So that'll kill you. And that's another piece that we need to kind of keep in mind as well. Someone always inevitably asks me the question right at this point, what about that whole PAE thing? Do we need that? That's completely different. PAE was a way that the developers in Windows were able to take us beyond the 4 gig limitation of RAM by actually changing the operating system quietly to not be a 32-bit operating system anymore. It became I think it's 37-bit, 36-bit, something like that, to get up to 64 gigabytes. And that was turned on automatically, not instantly, not when that was first released, but then once the data execution prevention became default, then it automatically had that this turned on so you could see 64 gigs. Nothing to do with anything of this stuff up here, and that I think that's probably kind of important to understand as well. So anyway, what do we do now, right? We've caught the culprit. We've found the tag that's leaking. What do we do? Well, if it's some vendor out there, call the vendor, get them to fix the product. If you're the person who wrote whatever this is, then you may need to go fix the kernel side of your code, and at least you know what side it is, not your user mode portion of whatever program it is you wrote that's causing this leak. It is the kernel that you're having trouble with. So you'll need to go and look at your filter driver or whatever it is you wrote that's leaking, but now you at least know what your tag is, and you can go find it and go figure out what code needs to be done. But one way or the other, there is a limit limit to how big the virtual address space can be, and you can't go beyond it unless you're on a 32-bit system, you're running out of your page pool, and you legitimately need more page or non-page pool, and you are willing to move to a 32-bit operating system and get that huge amount of upgraded space there. If you're leaking, don't do that. Go fix your leak. If you just legitimately need that space, go and get yourself more space on a more modern operating system with a 64-bit virtual address space. So that'll get you with that. But there's really not anything else you can tweak in the OS, realistically, that's going to make this problem any better. So I've got some good news. This is the end of the memory pieces for the traditional part of the performance series. We'll probably come back and loop around to some advanced topics on stuff like this when we end the proper part of the series and we get into advanced topics, which is still in the works and on the outlining board and hasn't been filmed yet. But we're at this point now where we can move on to another topic. We'll be talking about processors next and memory. Networking as well. The reason memory took so many episodes and such long episodes is because memory is a very complicated thing to troubleshoot, not so much beyond the reasons that we have multiple kinds of memory. Remember, so we've covered the RAM, we've covered RAM and page file together, we've covered the virtual address space for user mode, we've covered the virtual address space for kernel mode, we've covered process analysis and usage on things like working set and committed bytes, and so all of those things wrapped up together is the discussion of how to troubleshoot memory in Windows, and that's why it's such a big topic. But again, that's the good news. We are officially done with memory and can move on to other topics. So anyway, folks, this has been Chris with Microsoft, and as always, thank you a ton for watching. If you did find anything about this video useful or interesting, please take a second to give it a quick like. That helps other people to find topics of similar interest when they're doing searches in YouTube. Also, feel free to subscribe to my channel if you want to be notified whenever I do post a new video in this series or any of the other series such as Let's Tech, which is another active running series that we have. Also, my blog is at 9z.com. It's real super easy to remember. It's just the last number followed by the last net letter .com, which has also got links to my Facebook and my LinkedIn, my Twitter, and my TechNet blog. And so again, as always, thanks a ton for listening. I'll see you all in the next episode.